Assalamualaikum warahmatullahi wabarakatuh to everyone and the lecturers. Today we are going to explore a very important connection in algebra, how functions and graph are actually special cases of a broader mathematical concept called relations. If you look at the diagram on the slide, you will see a large outer box labeled relations. In mathematics, a relation is the widest possible category we use to pair numbers. It is simply any connection between a set of inputs and a set of outputs. There are absolutely no strict rules here. An input can point to one output, two outputs, or even a whole group of different outputs at the same time. However, notice the smaller circle sitting completely inside that big box. That circle represents functions. A function is a highly disciplined, restricted subset, or a special case of relation. It earns this special title by following one golden rule of uniqueness, which is every single input in your domain X must map to exactly one unique output in your range Y. To see this clearly, look at the arrow maps on the right side of the slide. The general relation breaks the function rule because the single input letter A splits off into two different destinations at once. The function map, on the other hand, shows a perfect, clean path where every single input goes to only one destination. This proves our core point. All functions belong to the relation family, but a relation has to be completely predictable to qualify as a special function case. Now, let's take these definitions and look at them visually. A graph is just a physical picture of a relation. It takes our ordered pairs of data and plots them as coordinates on a grid. But just like equations, a graph is an excellent tool because it can instantly show us when a relation crosses the line to become a special function case. To prove this to our lecturer, we look at the two graphs on the slide and apply a simple visual test called the vertical line test. Look at graph A. On the left, it shows a perfect circle, which represents a standard general relation. When we drop a straight vertical line right through it, the line cuts through the shape at two distinct points, which is the top and the bottom. This tells us that a single input value on the bottom axis has two different output heights at the same time. Because it hits twice, it fails the test and cannot be a function. Now look at graph B on the right. This smooth, wavy curve represents our special function case. No matter where you decide to slide a vertical line across this grid, it will only ever cross the curve at one single point at a time. This gives us instant, undeniable visual proof that every input has exactly one output, making this graph a true visual function. Let's bring this mathematical theory down to earth using a real-world example, the gym membership flowchart on the slide. This system uses the formula fx equal to 50x plus 100, where x represents the number of months you stay, and fx is the total cost. Even though this formula sets up a relation between time and money, let's look at the math to see why it is specifically a function case. Let's run a calculation for a 6-month plan to see how the machine processes the data. Step 1 is our input, where our domain value is x equal to 6. We feed this single number straight into our function machine. Inside the machine, the math follows a strict step-by-step order of operations. First, it handles the multiplication. $50 a month times 6 months gives us $300 in accumulated monthly fees. Next, it moves to the addition, adding the flat $100 sign-up fee to that amount. 300 plus 100 outputs a final definitive total of $400. If you look at the growth graph below the flowchart, you can see how this looks visually. The line starts at $100 on day 0 and climbs perfectly straight. When you look at month 6 on the bottom axis, it matches up with exactly 1 point on the line, $400. There is no second price option, no surprise fees, and no confusion. A single input gives us a single output, proving this real-world model is a perfect function case. To wrap everything up, Let's review the main takeaways of our presentation today so we can see the big picture. First, we have shown that functions and graphs are not random, isolated topics. There are specialized, orderly subsets built inside the broader universe of relations. Restricting a relation to a single output function is incredibly useful because it allows us to create predictable, real-world models. It completely eliminates guesswork, allowing businesses to budget costs and software developers to write reliable code. Second, we prove that graphs gives us a clear visual map to identify these boundaries, allowing us to use quick tools like the vertical line test to verify if a system is mathematically stable. Finally, for academic integrity, I want to formally cite our source. The core definitions, structural hierarchy, and educational flow used today were directly adapted from the excellent framework provided by the Rhode Island's Department of Education Office of Instruction, specifically from their unit study titled Functions and Graph. Thank you so much for your time and attention today. Wassalamualaikum warahmatullahi wabarakatuh.